And it's a great pleasure to have Eva Miranda from the University Politecnica de Catalonia. And she's very much an expert in dynamical systems and symplectic geometry. And the title of her talk this morning is Chaos by Nature, Trajectories of the Undecidable. Let's welcome.
Thanks a lot. I'd like to thank the organizing committee for inviting me to give this talk here in this conference. It's a pleasure to be in a conference that precisely makes a mixture of mathematics, physics, and computer science, and that's what this talk is about. Well, this talk is in the session of symplectic geometry because there's going to be symplectic geometry. There's going to be contact geometry, but if you don't know things about symplectic geometry, I try to keep things quite basic. Okay, so I spent a lot of time with this first slide, and this wants to represent, we have the dragon, and we have chaos. And here in the Chinese culture, the dragon is like the yin and the yang, so the dragon represents the order. Among the chaos here, we have some water, we have some chaotic orbits, and the talk is about this, precisely. The talk is about talking about chaos, but in a logical way. We're going to look at different sorts of chaos, and we're going to relate this to symplectic contact geometry, and I'll also talk about Navier-Stokes. A lot of things for 15 minutes. So let's start with David Hilbert. David Hilbert, it was the opposite of chaos. David Hilbert said, we must know, we will know. And that's the sentence he said before his death. And well, so David Hilbert had a very intense program of formalization of mathematics and about certainty of mathematics. And at that moment in Göttingen, many people were visiting him for inspiration. John von Neumann was visiting in the 27, 28 in Göttingen, and so was Alonso Charge. Okay, there is a rubber duck there. We'll see that the rubber duck has some connection to this talk. We'll see in a minute why. And there was also Robert Oppenheimer there visiting at that moment. Now, what do these people have to do with undecidable events? Well, what I want to talk today is three different stories that have to do with the opposite of certainty, have to do with uncertainty and with the idea of chaos. And the first story is going to have as a main character Alan Turing. And Alan Turing is also connected to the former line. Second story is going to be classical chaos. And then I'm going to mix these two ideas with fluids and Navier-Stokes. And we'll talk about the idea of chaos in fluid dynamics. So I mentioned Alonso Charge. He was in Göttingen to learn from Hilbert. And indeed, Charge was the PhD advisor of Alan Turing. And Alan Turing was well known for many things. Well, he is now a national hero, but he was not during his life, his very difficult life. He played a central role in breaking the Enigma code at the Bletchley Park. And his legacy in computer science has been honored a posteriori by the most well-known award in computer science, which is the Turing Award. However, all this work remained secret for decades. In particular, he was alive, so his death was not dead as a hero. But now we want to talk about something that Alan Turing found impossible, or rather possible, which is answering a question that was pending at the beginning of the 19th century, which was at the beginning of the 20th century, which was which problems admit a yes-no answer. And the halting problem was a problem which was in a to-do list, okay? And that was the problem he was dealing with during his thesis. Okay, and the question that he had to answer during his thesis is there a general recipe or an algorithm that tells us whether a process, an arbitrary process with certain input, will hold or not in finite time? So will it stop or will continue forever? And it was not known whether the answer to this question was yes or no. Now imagine maybe you have a thesis problem that you don't like and you have to struggle with it. Imagine that you have to solve such a thesis problem. It looks very strange. However, Turing proved in 36 that the halting problem is undecidable. What does it mean, undecidable? That it does not admit a yes-no answer, okay? So in order to prove this, he proved this by contradiction. And in doing such a proof, he came up with a definition, with the first definition of what is known a posteriori as a Turing machine. You don't put the name of yourself to the things you do, okay? But somebody else put the name. Like a Turing machine is exactly an abstract model of computation. Okay, well, Neumann then did the first, if you want, the first computer, right? But the first abstract model was done by Turing in the proof that the halting problem is undecidable. So we could say that he was the father of modern computer science. Okay, so now I come up with a story that it looks like doesn't have to do anything with this talk. I'm going to talk about rubber ducks, okay? And the idea of the rubber ducks is going to allow me to illustrate the notion of undecidable events, okay? I'm going to tell you a story, so be patient, and then we'll connect it to this idea of undecidable events. In 1992, there was a carrier, the Ever Laurel, which departed Hong Kong and was going to Tacoma, and there was a terrible storm, and it lost the cargo, completely the cargo. In particular, it lost a number of rubber ducks, more or less 29,000 rubber ducks. These rubber ducks have been lost and have been they have been found in places that you wouldn't expect, okay? Here you have a map of where the trajectories of these rubber ducks, okay? Some of them appeared in Alaska, okay? 10 rubber ducks appeared in Alaska in November. This was lost in January of the same year. And then on the news, on the British news papers, it was mentioned in 2007 that thousands of rubber ducks will appear on the British shores. Okay? Indeed, there is an advertisement of a, I cannot say what is the car, that explains this story. Okay? But indeed, all these British people waiting for the rubber ducks. And just one rubber duck showed up in Scotland. I will not make more comments about why in Scotland. Well, that's the fact. One rubber duck showed up in Scotland, and many others were expected. Okay, there is even a book that I have to buy. I confess I don't have it. It's the Mavi Duck that explains this story. Okay, so the lesson to learn here is that it was quite undecidable to know where these rubber ducks would appear. Okay. And there is some science behind the story of the rubber ducks. Indeed, there was a computer program, a computer simulation program to find objects lost in the ocean, and it was called the Ocean Surface Current Simulation, and it allowed to learn things about currents. And this was developed by a scientist, by an oceanographer, Jim Graham. And then Curtis Ebers-Meyer was not really a scientist. He was working on science like an aficionado in science. He was interested in it. And he joined Jimmy Graham in these studies. And they did a lot of experiments. For instance, they were throwing bottles, empty bottles with message inside a bottle. You've seen these horrible films where there are love messages in a bottle. Said, oh, I'm in love with you. What do I say? Instead of telling you, I'm going to send, to throw this empty bottle with a message, I love you, and then you get the message. Okay. Well, you must know, first, that this is not ecologically correct, and secondly, that only 2% of the messages on a bottle are recovered, according to this scientific study. So, and indeed, just one of those percent of the messages is a yes answer to the proposition. So, okay, how do they know this? Well, because the message was not I love you, but the message is if you get this bottle, you get $50, and this is a good reason to ask for the money, okay? So, indeed, it's quite uncertain, right, to get back these rubber ducks. It's so uncertain that I have to tell you that I brought 2 rubber ducks here, and they are in the hotel. So this morning I forgot to bring them here. I have a Scottish rubber duck and my rubber duck that I usually put in my purse in the middle of my talk. And it's so undecidable that it came all the way here from Barcelona, but now they are there in our beautiful hotel. Okay. So what does the rubber ducks have to do with Alan tree? Well, the summary is, well, this method of course used by Graham and Emmesmeyer could not localize all the lost rubber ducks. Remember, only 2% of the messages in bottles are recovered. So the question is, what if finding the rubber ducks is undecidable? So it's an undecidable problem. Of course, this is going to be like a metaphor for my talk. Okay, these rubber ducks are probably, in some of these plastic tanks in the middle of the ocean. So the question is, can we associate a Turing machine or a supercomputer to the trajectories of the rubber ducks? Okay, because then, because we know the whole thing is undecidable, then it means that finding these rubber ducks is undecidable. The association of the Turing machine to the movement of the rubber ducks has to satisfy a number of conditions. I'll get technical in a minute. So that's what the question I want to answer today, okay? And I want to answer this question with viscosity and without viscosity. Without viscosity, it's usually easier because it's the Euler. You have the Euler equations behind the fluid dynamics. And with viscosity, it's much more difficult. It's the Navier-Stokes problem. But today, I will provide a construction of a Turing machine to both a fluid with or without viscosity. And this is a new result that we just posted on the archive, indeed, just before coming here last week. So now I want to relate this to classical chaos. This is another idea, right? Classical chaos is the idea that by very tiny modification of initial conditions, the outcome can be very different long term, right? So this is the title of a talk, which is indeed much more fascinating than mine. That's the flap of a butterfly wing in Brazil set off a tornado in Texas. That's the title of a scientific talk by Edward Lawrence in a conference, okay? And indeed, this is connected to the idea of chaos that you all know. Okay? And as you know, chaos was discovered by Lawrence, and indeed in the group of Lawrence, I must say, there were also Ellen Fetter and Margaret Hamilton who were developing all the computations that yield this accidentally the discovery of chaos during studying one of the problems in meteorology. Okay, the equations are as simple as that, but it's interesting to see that for certain parameters, the system is chaotic, and for other parameters, we have periodic orbits. So chaotic systems are very interesting. And if I could have to, well, we have to define what is chaos. Well, we can use the definition of Lawrence. Chaos is the following idea: when the present determines the future, but the approximate present does not approximately determine the future. Okay, so just modifying time initial conditions give different solutions long. Now I want to say that this idea of undecidability, which is a difficult word to pronounce, is also a new form of chaos, but it's a different sort of chaos. It's not that we don't know the position of a certain event with precision, the movement of a trajectory with precision, but rather that we cannot know because there is a logical barrier. Okay, let's go there. But before we go there, remember that just some months ago we were all very worried about I-4R. This was an asteroid. We were just, we were living with our lives, and out of the sudden, we were all very worried. There is an asteroid that may fall down, right? And then at some point, we looked at the map, and they said, oh, okay, it's far from where we live. But everybody was very concerned, and, well, this would be the asteroid. And then there were some studies, right, that, of course, we're using perturbation theory, right, where this asteroid could fall. And the probability spiked on the, well, here there was a representation, well, it's a simulation, but this is not working because it's a PDF. But the spike of probability was 3.1 on the 19th of February, okay? So this is indeed quite a lot. But okay, if we put it in perspective, will we die from an asteroid? Well, asteroid impact versus other causes, and I'm not getting political here. But, well, if you fall from height, or choking from food, or from a bicycle accident, or even from sunstroke, it's more probable that you die from that. Okay. Now we'll get back to this idea of the asteroid. The asteroid is going to be there in the rear with the rubber ducks, this crazy idea, because we know that there is some chaos related to the movement of the asteroid, right? The question is, which sort of chaos is that? We know there is classical chaos, this is proof. We know there is classical chaos in the solar system, this is proof. Now the question is, there some other kind of chaos, like logical chaos? We'll get back to that. Well, remember that we keep on, it's better not to watch news or not to pay attention to the news because we get nervous. Then can we relax? Then we were relaxing about that, okay, the probability, it was close to 0, but then there was a Soviet satellite that could fall, and if you were in the UK, it was going to fall in London. If you were in Spain, it was going to fall in Girona, okay, and it was quite scary. And finally, of course, it landed on water. So this was in May. This is quite recent. So can we relax? Yes, but not so much. And now we go from heaven to the waters, right? Now I want to ask this question of complexity in fluids, okay? And complexity here means two types of complexity, dynamical complexity and logical complexity. Today I want to focus more on logical complexity, though it's very interesting to understand what the connections are. So, well, first of all, we have evidence that fluids sometimes behave in a way we cannot expect. So the question is, are fluids complicated enough to even perform computations? Can we associate a Turing machine to the movement of fluids? That's the question. And fluids with viscosity and without viscosity. Today we take all these cases into account. Well, this is an interesting question, but especially if it's a Nobel Prize to ask this question, right? This was Penrose. Well, Penrose was not really asking this question. Penrose was interested in the limits of computation and if physical systems could compute. And later on, this is Chris Moore, he asked again this question explicitly, can fluids perform computations? And later on, this is Terence Tao asking again this question. He was asking this question because he wanted to construct a counterexample to the regularity conjecture of Navier-Stokes equation, one of the problems on the playlist. And we'll get back to that. So that's the question we want to answer. Can it perform computations? And okay, if we look at the computational models, let's go to the one of Turing. Can fluids simulate any Turing machine? That's the question. Okay? So the answer to this question is yes. Okay? And I'm going to prove this. I'm going to use the result of Moore. Again, I'm putting two examples of PhD thesis, totally successful, Alan Turing and Chris Moore. Chris Moore was doing his thesis on a problem concerning the Cantor set, okay? And then one day he woke up and he read in the newspaper, mathematician discovers a more complex form of chaos. That's the kind of title we all want to read when we do a thesis. This doesn't happen, you do your thesis, you defend, nobody knows what you have done. But here is Chris Moore. So mathematician discovers a more complex form of chaos. And this more complex form of chaos is precisely this logical chaos. So what Moore did was to associate a Turing machine, okay, to a dynamical system on the plane. That's what he did. So this was probably one of the first associations of a dynamical system of a Turing machine to a dynamical system, and he understood when this association could be good enough, okay? And good enough, so when this association is such that you can associate any Turing machine, so a universal Turing machine, and this concept is known as Turing complete. So indeed, the answer to this question is very simple. He characterized systems, so in dynamical system, Bernoulli shift is well known. So what he did is to completely characterize which dynamical systems in dimension 2 can have associated a Turing machine. And the answer is, instead of a Bernoulli shift, what you need is what he called generalized shift. Okay? So Moore generalized the notion of shift, and the characterization is you can associate a universal Turing machine if and only if you can associate a generalized shift to your dynamical system. And the generalized shift he characterized in terms of a kind of puzzle on the square Cantor set. Okay? So he said a generalized shift, okay, a Turing machine, my dynamical system can be thought as a mapping from the square Cantor set to the square Cantor set, satisfying a number of conditions. Okay, and this is the picture that we could read on the newspaper. So it's time that I define what a Turing machine is, because I said blah 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 Turing machine. What do we need to know today about Turing machines to follow this talk? Very little. I want you to think of a Turing machine as a printer. Okay, a printer that prints states on a long tape. We all have this image of Turing machine as a very long tape, infinite tape. With here I'm going to put zeros and ones. This is my alphabet. I could have some other symbols, but I want you to think of the Turing machine as a printer of states on this long tape. And I can always assume that the alphabet is zeros and ones. And among these states, I have two very important states, the initial states, and then what is called the halting states. When I print the halting states, the printer stops. So, well, because I have a printer, I need to have a user guide of the printer. The user guide of the printer tells me how this Turing machine really works. And how does it work? Well, that's the definition of a Turing machine. The user guide is what is called the transition function. Okay, so the user guide is just a transition function that associates two pairs of states and tapes, states and new tape, and it tells me, and an epsilon, which can be -1, 0, or 1, which tells me if I need to move my tape when I print, if I need to move the tape to the left or the right. I'm going to give you an example rather than definition. So here I have this first tape here, and I'm printing the state Q0, okay? Now it goes to Q prime 1, okay? And I have this +1. This +1 tells me that the printer, okay, I'm going to replace this 0 by 1, okay? And here it's a bit, it doesn't follow the intuition because the tape is going to move to the left, you see. However, the printer moves to the right. So, okay, this is this +1. Here I had a representation, but because it's a PDF, you cannot see the animation. But this is what is a Turing machine. And now I want to convince you that the Turing machines are closely related to the square Cantor set, right? So I'm going to, and how to do this? I have my Turing machine here, okay? My Turing machine is working, and what I'm going to do is I'm going to take a picture of my Turing machine. I take out my phone, and when it's working, I just make a snapshot of the Turing machine. So when I make a picture of the Turing machine, what do I see? Well, I see some state, the printer, okay? And I see where I am, exactly. So I see a concatenations of zeros and ones, okay? So well, what I do is to consider this collection of zeros and ones, the one on the left, well, I have infinite numbers, and I consider them as coefficient of the ternary span. And the one on the right, the same, some coefficients of ternary span. So this, what does it give me? Well, this gives me a number that indeed it's on the counter set. So this is just plug the numbers on the left as coefficients of a ternary span and the numbers of the right. This gives me two numbers which are on the counter set. Okay? So I take this as the x and the y, and well, so this is this red point, okay? And this red point is on the square counter set. So what is the lesson to learn? It's the same to take a picture of a Turing machine in action than to put a point on the square counter set. So now I let this Turing machine continue the work, and I keep on taking pictures. What's going to happen is that this red point is going to be jumping on this square counter set. So I can look at this as a discrete dynamical system, as a mapping from the square counter set to the square counter set. Okay, so a Turing machine, I can think of this as a mapping of the square counter set to the square counter set. Okay, and I can think of this as a dynamical system, discrete dynamical system. And now I have to make the exercise of going backwards. Now I have a dynamical system, and I want to associate to it a Turing machine. Okay. Well, in this association, one of the things that Moore did, okay, Moore precisely, he had this idea of, okay, I think of a moment of computation of my Turing machine as a point on the square counter set, and as the computation goes on, this point is going to be moving. But not only that, okay, he characterized how this mapping has to be so that this Turing machine is universal, so it can simulate an arbitrary Turing machine. And well, this is technical, but the condition, this is the condition, okay? He proved, this is a fundamental lemma, where he proved that, well, this mapping, okay, this mapping between these two square counter sets is the restriction of piecewise linear maps, which are area preserving, okay? And this is where symplectic geometry starts to show up. So this is connected to area preserving maps on the square, okay? Okay, he was working with mappings from the counter set, the square counter set, but we could also extend this to a mapping, to a differentiable mapping, to a smooth mapping on the disk. And this is the kind of game I'm gonna follow. So we need to jump from discrete to continuous dynamical system. So what does it mean that I have a way to associate a Turing machine to a dynamical system? The idea is clear. Each time I make a computation, okay, I'm going to try to make an association such that each time I make a computation, my dynamical system, here I think of here the dynamical system was just a map. Here I think of the dynamical system as a trajectory of a vector field, okay? And as this point advances here, this computes. Of course, I'm associating a continuous dynamical system to a discrete dynamical system. So many questions pop up. When is this association good? Well, I say this association is good or Turing complete if this association is such that my vector field can simulate any Turing machine or a universal Turing machine. And how do I do it? The definition looks very strange, but with the idea of the rubber ducks, you will understand. I fix an open set here, okay? And I said that this vector field is Turing complete, okay? If the trajectory, the association to the Turing machine is done in such a way that when the trajectory enters here, the Turing machine falls. You think, okay, what about the rubber ducks? Now imagine that this is the trajectory of a rubber duck. Imagine that this neighborhood is a neighborhood of the UK, okay? So the holding of any Turing machine is equivalent to the rubber duck entering a neighborhood of the UK. And because the faulting problem is undecidable, it's undecidable to know whether the rubber duck enters this neighborhood of the UK. Okay? So that's exactly the connection. But you need to think of the rubber ducks as a metaphor, of course, but it's quite practical. So that's the technical definition, and of course there's a lot of work, but that's the idea, that we have a good notion of associating a Turing machine to a dynamical system. And now let's talk about money, okay? Let's talk about $1 million, which nowadays is not as much as it used to be, okay? And let's talk about the list of pending problems on the clay list. Well, these are the Millennium problems, and we mathematicians, so far, we only proved the Poincaré conjecture. This was proved by Grigori Perelman, who didn't pick up the prize. That's the summary of what mathematicians we are. And now, out of this problem, I want to look at the Navier-Stokes equation, though it's quite connected to the B versus NP problem too. I'm going to look at the Navier-Stokes equation problem, and I'm going to see how can this be related to what I'm talking about. Well, the Navier-Stokes equations are equations that model the movement of fluids that are incompressible, okay? So you cannot compress them, and have some viscosity, okay? So the fact that they are incompressible, this is related indeed to contact geometry. We think of the Navier-Stokes problem in 3 dimensions, so this is related to contact geometry. Any 3-dimensional manifold admits a contact structure, and the idea that there is this equation, and there is the equation that the divergence is free, which means that the flow, okay, preserves the volume. So this is also connected to contact geometry. We'll get to that. And these are the equations of Navier-Stokes. Here we have the viscosity, okay? Here we have some external force that sometimes we, in a theoretical way, we can absorb here somehow. And we have an evolution in time. So this is a partial differential equation, okay? And what is not known is whether, things are known about local behavior, but not long-time behavior of this equation. So the problem, the Navier-Stokes problem, in a nutshell, would be the problem to determine whether, for all initial conditions, where these initial conditions are not any because they have to be physical, so they have some Schwarz conditions associated to them, that for any initial condition, the evolution gives me smooth solutions, or if I'm going to have this kind of singularity or blow up, that from a physical perspective is quite surreal, because it tells us that there are regions of a space where the energy of the fluid becomes concentrated to the point of becoming infinite. So if there is the effect of blow up, this will tell us that these equations are not physical anymore, because it doesn't make sense that right now with this we have a tsunami here. Okay? It's a way to keep out of the top, but okay, it's not realistic. So, okay, that is the idea, but if you want to really, okay, I want to get this $1 million, these people have not done anything, well, there is a lot of work these days on these equations. You can go to the clay list, and this is the way Pfefferman describes the problem. We have the 2 equations. The second one is the divergence free, and the first one is the equation I was showing. And we have some initial conditions, okay? And then you solve the problem, whether you prove that there is a smooth solution for all t, or you find the blow up. And there are 2 scenarios of the problem. The first one, well, these are the conditions that you need to impose on the initial conditions. They are physical, so you have some bounds, okay? And there are 2 scenarios. The scenarios with symmetries, so you think that this happened on a 3 torus, and without symmetries, so you are thinking on R3, okay? So this is the statement, okay? So again, the scenarios are existence or breakdown of Navier-Stokes solutions. So this problem, as you know, is still open, okay? And in dimension 2, this problem was solved a long time ago by Olga Leidissenskaya in 58. She proved that the answer is yes, there is a smooth solution. And indeed, she struggled quite a lot with three-dimensional. Even there is a book by Olga, but the problem is still not solved. And as we heard yesterday, maybe the answer will come from formalization and machine learning. We'll see. Okay. So why are we talking about these kind of problems of logical chaos and so on related to the Navier-Stokes? Well, because Terence Tao had, I made an error, Terence Tao, working hard here, had a nice idea to attack the problem. And the nice idea is to think of matryoshka. So you have a Russian doll, you open, you have another Russian doll, and so on. And it's the idea of symmetry. Indeed, Terence Tao proved that some equations that are called the average Navier-Stokes equations do exhibit blow-up. And he did that proof, indeed, by associating to it almost a Turing machine, some kind of logical gates. And then what he wanted is to take this idea to the Navier-Stokes equations. But the average Navier-Stokes equations are very far from the Navier-Stokes equation. So it didn't work as well. But his question is, can we create some initial conditions that are very complicated and have all these symmetries? And he thought of this idea as having some initial conditions which are Turing complete, okay? And indeed, he asked, can we find some initial conditions which are solutions to the Euler equations and Turing complete? And that's the question he asked. And then that was the first question. And then the idea was, okay, because they are Turing complete, they are very complicated, maybe this leads to blow. Okay? So the answer to the first question was yes. And the answer to the second question is, unfortunately, we provided a Turing complete Euler flow, but unfortunately, it doesn't lead to blow up. Otherwise, we would have this $1 million. Okay? So what's the story? In 91, what's the summary? Let me see. I still have time, right? Good. So the summary is, in 91, Moore asked if hydrodynamics or fluids are capable of performing computation. There were 29,000 rubber ducks lost in the ocean in 92. 2009, a rubber duck shows up in Scotland, and the rubber duck is in my hotel at this moment. In December 2020, we proved with Robert Cardona, Daniel Peralta Salas, and Francisco Presas that there exist stationary Euler flows in dimension 3 that can simulate any Turing machine. And I'm going to call this construction the fluid computer 1. Of course, you don't call your theorems fluid computer because it's very fancy. But then you talk, then I had an interview at El País, and then you talk to somebody who really knows how to put fancy names. And he said, no, Eva, what you have done is a fluid computer. Okay. After that moment, I talked to Manu Asede. I call fluid computer the construction. So we produced a fluid computer 1. Where is your fluid computer? It's abstract, like the one of Turing. I don't have in my office such a fluid computer. Okay? But I plan to have it. That's my dream. Okay, but constructing is an issue. Stability is a problem. So, and then, indeed, I had to give this talk here, right? And we had this proof. We knew how to prove it, and we were working with this with one of my current PhD students, Soren Dier, with Ángel González Prieto, and again, Daniel Peralta Salas. And we had the construction, but then I said, look, I need to give a talk in China. So last week, we posted on the archive. So, and that's the new result. And this is the first time that this is explained, that there exist stationary solutions, indeed, of the Navier-Stokes equations, which are Turing complete. And this is indeed quite interesting, right? Because everything you say on Navier-Stokes, right, it's much more interesting. Well, it's as much interesting as Euler, but it's a bit more complicated because you have viscosity. So let me explain the constructions. And constructions have a pattern, a geometrical pattern, both of them. Because you don't know, but I am a geometer. Like I have been talking about chaos, about dragons, and so on, but my life is as a geometer. So the proof is geometry, okay? So the first fluid computer, the one that is Euler, the solutions, Turing-complete Euler flows. This is done using contact geometry. Indeed, this is contact geometry, and indeed, the flows are given by the red vector field. And this is the fluid computer number 1. And the fluid computer number 2, which is the Turing-complete Navier-Stokes flow, also has a geometric structure behind. And that's new, and that's quasi-symplectic geometry. And also, the vector field has a meaning there, and it's also called the red vector field. It's the same name, red vector field. So, why it's so geometrical? The idea is the following. Whenever you have Euler flows and Navier-Stokes flows, I don't know if it's going to work if I move there. Is it going to be there on the screen? He's not listening. So let's see, well, whatever, who knows. If they don't see it, you see it, and you are privileged. It's good for you. Okay, so we have a vector field. There's going to be a vector field. The secret is there's going to be a vector field, okay, which is going to be a solution of this either Navier-Stokes and that this solution is going to be stationary. I'm going to say it in a minute what it is. It's going to be stationary solution to either Euler or Navier-Stokes. And then we don't say it, but there is a metric whenever we have a physical problem. And this metric is the Euclidean metric. But because I am a geometer, I'm going to allow myself to change the metric if necessary. And I think that I have a three-dimensional manifold with a metric. And then I'm going to show what is the main character of the geometry here. It's going to be a one form that comes from contraction of this stationary solution with my metric. And this one form is going to have the magic property that it's either a contact structure or a quasi-symplectic structure. Okay? So indeed, I'm going to have a kind of mirror. And I'm going to go to the slides in the mirror, that there is a kind of mirror that tells you that it's the same to have contact manifold plus metric. So on one hand, I have contact manifold with a contact structure. And on the other side, alpha. And on the other side, I have a metric. And when I modify the metric, I modify the contact structure and vice versa. Okay, so there is a kind of mirror, okay? And here, I will have a red vector field. And on this side, this red vector field, after reparametrization, is going to become the stationary solution. And this stationary solution, in the Euler case, is a Beltrami vector field. And that's the new thing I need to say today, is that if the structure is quasi-symplectic, contact, we saw it before, in dimension 3, contact manifold is this condition. Okay, different from 0. And in dimension 3, quasi-symplectic structure is the condition on the boundary of contact. So if I take all the structures of contact, of all the contact structures on the boundary, I'm going to have quasi-symplectic structures. And there, I also have a metric, okay? And the vector field I take here is red, and the vector field I take here, big surprise, is going to be an harmonic vector field. Because harmonic vector fields are stationary solutions of Navier-Stokes equation. And harmonic vector fields up to reparametrization are going to be red vector fields of the co-symplectic structure. Okay, that's the idea. So that's the secret blackboard that maybe nobody saw on the, but so what I want to do indeed is, this is the idea I want to use, but this is in dimension 3, and I want to do things that are Turing complete. Okay? Then what do we know about Turing completeness? Very little things, but we know one construction that is Turing complete, which is the one of Moore. This construction is a construction on the square counter set, so two-dimensional. And Navier-Stokes and Euler are in dimension 3. So we need to go from dimension 2 to dimension 3. What is the first idea that comes to your mind? If I have a vector field, how do you go from 2 to 3? Or from 3 to 2? Poincare section, right? So think of the Poincare section idea, which is a very naive and primitive idea. It relates dynamics in dimension 3 to dynamics in dimension 2. And now I take the idea of Poincare section. So what I want to find is a vector field, okay, whose Poincare section is exactly the mapping of Chris Moore. That's what I want to do. And this was the first idea that we had, and it works. This is rare. Usually you have ideas and they don't work. It worked. The proof is very simple. You look for a vector field whose time one map, with a flow whose time one map gives you the mapping of this mapping. Okay, there are nuances. This mapping is discrete. You need to extend this mapping, okay, to a mapping of a disk that has some good properties, okay, because you need to go from discrete to continuous, and because you are going to be working with contact geometry and symplectic geometry, you want this extension. You need to extend this to a disk, and you want this mapping to be area preserving. This is an important feature. Once you have this, well, you work it out and it works. You find your vector field. So what's the secret weapon here? There is a secret weapon. The secret weapon is what is there on the blackboards, and is the fact that, well, these are classical Euler equations, so viscosity 0, and I look at them geometrically with a Riemannian structure, and then this derivative is the covariant derivative. We like it, okay? And then I look at the stationary solutions. This is something that puts people in analysis very nervous. You say, I'm here for the PD, and now you show a stationary solution. Well, it's enough. I have a stationary solution that is Turing complete. Okay, then we also work some time-dependent constructions, but it's not the object of my talk today. And, well, what I explain here in this slide, indeed, is this first correspondence here, that this first correspondence between contact manifolds and stationary solutions of the Euler equations and a particular type called Beltrami fields. Beltrami fields are vector fields parallel to its curl, which are divergence free, okay? And they are famous for a number of reasons. In particular, your favorite example is Beltrami, usually. For instance, the hot fields on the hot vibration on the 3-sphere are Beltrami fields. The ABC flows are Beltrami fields. And these are stationary solutions of the Euler equations. But they have some geometry attached to them. They are Beltrami. On the other side of the mirror, reparametrized, they are red vector fields of a contact structure. And this magic mirror is a discovery in the contact case. Here I'm explaining what I explained there already. It's a discovery by Ednar and Reist, okay? And initially in the fluid computer construction one, we use this. So particular solutions of Euler equations are solutions to a geometrical problem. This was proved by Ednar and Reist. And then when Soren started his thesis, I said, well, Soren, we need to go farther. What happens? Do we have some geometry attached to the Navier-Stokes equations? And it turns out that we do have. And that structure is co-symplectic. Well, co-symplectic geometry, people don't like it as much as contact, of course, because on a 3-manifold, any 3-manifold admits a contact structure, and it's not true that every 3-manifold admits a co-symplectic structure. However, it's a strong weapon, okay? And on the other side, here you work with harmonic vector fields. Of course, when you think of harmonic vector fields, they are going to cancel out the Laplacian. So it looks like it's a kind of illusion. Indeed, this works for not only for a viscosity, but for any viscosity, because the coefficient in the Navier-Stokes equation is going to cancel out. So what did we prove? This is something like, okay, I'm giving a lot of information. This is something I already done. Okay, summarizing. I have indeed given the proof here on the very quickly, but summarizing fluid computer 1, using contact geometry, we prove, chaos. We prove there exists solution to the Euler equations which can simulate any Turing machine. And okay, what is the interesting outcome of this? That because the halting problem is undecidable, we prove that there exists undecidable fluid paths. This is something that was not known, so it's a new result. Okay, and we did it in the Euler case. And just very recently, we also did it in the Navier-Stokes case. But first, I'm going to quick now because I get very nervous. I want to explain many things. And it's time. No, I have 9 minutes. This finishes, what? 5 minutes. Okay, good. So question, did you get $1 million? Short answer, no. Okay. Why not? Okay. Well, these are Navier-Stokes equation. These are Navier-Stokes, okay? And then we constructed the initial solutions that Terence Tao wanted, Turing complete, Beltrami, blah, blah, and we plug them up. And the funny thing is that we can see how it evolves. And there is no singularity here, okay? So good news, yes, we answered one of the questions of Terence Tao, but news, it doesn't give a blow-up. So what do you do after that? Well, not only that, but the exponential decay tells you, that indeed this is not going to be able, you are not going to get from this construction a Turing complete Navier-Stokes flow. Okay? So now what's outside the Beltrami field? The Beltrami box. Okay? Well, chaos, right? According to this picture. So this is me inside doing Beltrami fields with Daniel Peralta Salas, very happy. And here is me trying to leave the land. And then you say, what's up? Well, I need a little bit of Chinese culture. Okay? So if you know the enemy and you know yourself, you need not fear result of 105. Very nice. Okay? Very nice. But do I know the enemy? Who is the enemy? Okay. Navier-Stokes, maybe. So at the beginning, and this is a little bit the idea of Tau, if you have some Turing complete Euler, you think of Navier-Stokes as a perturbation. But then people in computer science prove that it's not, the condition of being Turing complete is not stable by perturbations. So this means good for you that you have this Euler flow. You will never get from in Navier-Stokes. So this is your enemy. But then what happened is that we were working on this, we were working on the idea of associating co-symplectic geometry, some fluid dynamics of structure. And indeed, we realized later on, we were working with harmonic fields. We had proved that harmonic fields gives you exactly co-symplectic structure. And then one day, Daniel tells, oh, by the way, harmonic fields are stationary solutions of Navier-Stokes. I said, okay, then you have the Turing complete. Okay, so things always come after some work. And what we proved with Soren, who is here, Daniel Peralta Salas and Ángel González Prieto, is that first we can extend the mirror that Endar and Grice prove to the co-symplectic, and then on the other side, instead of Beltrami fields, you work with harmonic vector fields. So d alpha, you have a vector field which is the dual to a one form that is harmonic. So d alpha and d star alpha is 0. And then, so that's what we prove, the co-symplectic correspondence, okay? And the application of this is that, okay, if your manifold admits such a structure, that here, you know, we had to choose a name, and then it was 2 a.m. I said, let's call it Hodge. Hodge is classic. So if we have a Hodge admissible Riemannian three-manifold, there exists a deformation of the metric and a solution of Navier-Stokes equations associated to this deformation that is Turing complete for any value of the viscosity. So we don't have this problem that people in computer science have. Our construction is robust. Okay, so this worked for any value of the viscosity. And of course, I said it's good. I'm going to talk about it, but let's put it on the archive. You can find it on the archive since last week, 10th of July. Okay, that's the paper, and you can look. The proof is just 11 pages, and it's just the mirror is super easy. It's very simple. And what else? I have 2 minutes, no? 1 minute, 2 seconds. Okay. So what's next? Next has to be a fancy name. So we have fluid computer. Let's call it the hybrid computer. Okay, now I'm going to take the pieces of what I have constructed. Let's assume, okay, what I have constructed is suspension of dynamics. So I can think of them as a piece of cylinder. Okay, and on this cylinder, I have 2 different structures coming from Euler and Navier-Stokes, and I can try to glue them. Okay, and there we were one day, Ángel González Prieto making pictures, because there is something that does this, which is topological quantum field theory. So one thing you can do is to glue the constructions that you have to do something maybe more potent. And how you glued it, the topological quantum field theory, indeed, it's indeed following the ideas of quantum computing. Indeed, if you go to the lectures of computation by Feynman, the constructions of the first constructions of topological quantum field theory really are the definitions of how a quantum computer operates. So in a way, again, we need a fancy name. We call these fluid computers a basic unit of computation, fluid, qubit was taken, and then we glue them using topological quantum field theory. Okay, how do you do this? Formally, you do it defining a functor, okay? So this is something we did with Daniel Peralta Salas and Ángel González Prieto, and Arradoda, which is what we call topological clean field theory. So this is a new model of computation that what it does is to use the models, the fluid computers models, but in general, the flow of any dynamical system to compute, okay? And, well, so the main result, indeed, how do you define this topological clean field theory? So you define it as a functor. The first time I gave a talk about this, I say it's a functor, and then people just completely collapse. So it's better to say, well, you use the flow of a vector field to compute, and okay, as Ángel González Prieto will say, this means that this functor is full, and this is the main result of the paper, that you have, indeed, you have a category, you associate a computational category, okay, to a category. So you have a new way to compute, but it's abstract. And the model of computation that you take is that of partial recursive functions that were, okay, all the systems are equivalent, but they were created by Klein. And this is why we call this topological clean field theory, okay? And now the question is, why do you need a new model of computation? Well, because maybe it's better than the models you have. So we have like 3 questions we want to answer. The first one, Loa for Navier-Stokes, it's like a crazy dream. But as you see, Terence Tao visited us in Barcelona in September. We didn't solve this problem, okay? And, well, what about the new model of computation? Is it better than the models we have? Will the hybrid computer be the quantum supremacy? Now we are working on this, and we know that not exactly the topological clean field theory, but an improved version of it has chance to beat quantum supremacy. And the pending problem, let's go back to the satellite. What about the asteroid? So do you have undecidable events in celestial mechanics? This is something we are working on, but we are very far from understanding. So This would be the equivalent of having a rubber duck. And indeed, I had done with Sora. This is an animation, but it's okay. So you could see this moving. If you put a rubber duck on the asteroid, this would be the equivalent of logical chaos. Thanks a lot. With this, I finish my talk.
So quickly, maybe, do we have any questions for Eva?
Thank you for your great talk, Professor. My question is, are there any relationship between the mole transformation and smell horseshoe?
That's a very good question. That's indeed a key question. Very good, thanks for the question. So in dynamical systems, we detect chaos, classical chaos, when there is a horseshoe. This is what a smell will learn from a smell. If there is a horseshoe, you have chaos. So your question is, what is the analog of horseshoe? How can we detect this other type of chaos? Well, it's true that Moore said, the answer to your question is yes. Moore says, well, if we have this generalized shift, right, then in a way we have chaos. But this generalized shift is a construction that is not intrinsic, because you are associating a computation, an encoding to a dynamical system, and this is not intrinsic. So your question, indeed, is very good. Your question is, can you detect this undecidable intrinsically from your dynamical system in the same way you can detect classical chaos if you have a horseshoe? And the answer is, we're still looking for this characterization. This is one of the open problems that we posted on a paper that is on arXiv this week. You know, I was speeding up putting this paper before my talk. This is one of the open questions we are dealing with. Very good question.
Thank you.
Maybe if there's something very, very quick. Yes.
So, thank you, Eva. So, in your opinion, what is easier to deal with, oil or stocks?
That's a very good question indeed. Like, for a long time, we're thinking that the easier one should be Euler, but somehow it seems
But easier for what? For probing?
Easier for probing the blow up. No?
Blow up, yes. So that's.
Well, it turns out that you and I now know that the blow up of Euler will be proved before the one of Navier-Stokes, right? We were attending yesterday a talk by a colleague, Diego Cordova, who announced it at the end of his talk. He announced it very shyly, but in September probably we will have this proof. But in principle, indeed, viscosity seems to help for computational reasons. And I don't know this because, you know, I work with computations in a theoretical way. But people who are working on trying to find a counterexample of the Navier-Stokes with machine learning say so. Like, in a way, viscosity helps.
On showing
When you are using computational tricks, not theoretical proofs.
To build singular solutions.
To build singular solutions. But of course, like, we don't have this.
But this is a bit anti-intuitive, right?
This is the intuition, but of course this is not proof, because where is this proof?
Yeah, but intuition also says that viscosity should make things smoother. In some
exactly,
way, right?
That's the intuition.
Yeah, okay. Thank you.
But I don't know, I think like, it seems that the first, well, we heard yesterday, right, that maybe the first proof that we have of the blow up of Navier, because now everybody tends to say, yes, there is blow up. Indeed, we don't voted for that in September in Barcelona. We organized a conference. And of course, you don't vote for the results of theorems, but we did that. And I don't know, because Terence Tao, I don't know why, but opinion dynamics, maybe it tells us that the majority is that people believe in blow up, right, of Navier-Stokes. Now, maybe the first one, the theoretical proofs do not seem to be working, but because there are some proofs using the idea of user stability, but the proof is not there. It seems that maybe it comes from machine learning by plus formalization of mathematics, lean or some kind of things, but I don't know. It's very far from my knowledge, this. But all these people seem to say that viscosity helps.
Okay, well, if you have any more questions for Eva, please ask during the break. But let's thank her again for a very entertaining and engaging talk.
I'll show you